Okay, welcome back to Monday morning for another week of CompuCell. Today, we're going to be talking about something a little bit different, which is going to be network modeling. And the first part of the lecture is going to be really on networks generally and on modeling networks using the antimony modeling specification, the tellurium modeling framework. And it's not going to have much to do with CompuCell, CompuCell to begin with. As always, I need to remind people that the session is live streamed and recorded and made available afterwards. I also want to thank our funding sources. So today we're going to be focusing on networks, and we'll connect networks to cells more tomorrow morning. So we're leaving out this middle layer to some extent today. We're going to talk a little bit about networks in context of modeling. We're going to run a simple network. We'll talk a little bit about some of the different kinds of biological networks. And then we'll do a little bit about how to implement them as models using the antimony modeling language. And the reason we use antimony modeling language is it's very, very simple. You can learn it in 5 minutes, and that's a big advantage compared to a lot of other methods. We'll do 1 or 2 simple examples, and there'll be one that maybe will be a homework problem, depending on how much time it takes. There is a tellurium cheat sheet. Hayden can put that link in the chat, which explains the syntax for antimony and tellurium. I should say that network modeling is a big field in its own right. Herbert Sauro, who we work with a lot, teaches a summer course of network modeling, virtual summer course of network modeling. There are many other online courses you can find. I teach a regular term time course that takes a whole semester on this topic, and that's up on YouTube if you're interested in it. Slide decks are available online. And so we're only going to be able to cover a couple of examples of network modeling here today and tomorrow. In some years, we've spent more time on network modeling, particularly 2020, 2023. And if you look back at the YouTube videos and slide decks online, you can get more information from them as well. I want to talk a bit about networks in CompuCell. We see this hierarchical diagram a lot. Networks show up in 2 places in this hierarchical diagram. At the whole body level, where they typically represent transport of chemical species in the blood, and inside of cells, where they represent metabolism and control of the cell. And even though we're talking about the smallest and largest length scales in the body, the mathematical structure of the network is the same. If one wants to be technical about it, the whole virtual tissue model could be thought of as an interaction network, either a static interaction network of every possible interaction, or a dynamic network, which represents how interactions arise and disappear through the dynamics of the system. Here, we're really talking about nonspatial networks. What we're going to be doing are, conceptually, we have to define the kinds of networks we're going to be dealing with, their structure and their rate laws. We're going to have to relate network variables to cell scale behavioral parameters and variables. That's typically quite hard. That's one of the reasons that things like omics don't give you as much information as you'd expect, because, say, the level of particular molecular species may not tell you what the speed of replication of a cell is, for example. Then we have to make those concepts quantitative. We'll do that here with antimony, which is a way of implementing network specifications in computable form. We have to define parameter values. We're not really going to talk about parameter identification in this set of lectures. There's more in those other courses that I've talked about. Then we'll talk about how to load instances of networks into CompuCell, either into the objects, specifically cells, or the whole simulation. Today we'll only use the whole simulation one. And then we'll talk about how to write Python glue code to connect the variables and parameters inside the networks to the variables and parameters in the CompuCell multicellular model. Because that's not automatic, you have to do that by hand. As I mentioned before, and you've seen this slide previously, CompuCell3D supports network modeling in a variety of languages. SBML, System Biology Markup Language, Antimony, which we'll use today, MabBoss, which you'll see Wednesday morning, CellML, and BioNetGen. We're not going to cover SBML, CellML, or BioNetGen. If you're interested, there are online resources for that. I am not going to give you a lot of detail on this today, but I want to point out that BioModels, www.biomodels.org, is an online repository that archives thousands of network models. You can go to their homepage. I'd encourage you to do that. You can click on a model. It'll give you information about what the model is about, its documentation, its annotation. You can view a hairball diagram of what the model is, and you can go and download the code for it, usually in SBML. It's a great resource, but most of these models in BioModels were written in isolation, not for inclusion in multicellular contexts. And so in general, it's not so easy to just pull models from BioModels and use them. They'll run, but they won't do anything useful unless you learn how to connect them to CompuCell concepts. Resources for network modeling. Herbert Sauro wrote a fabulous introductory text online. It's tellurium.readthedocs.io. Strongly recommend going through all those exercises. Very, very valuable. Herbert also has a nice textbook, a very elementary textbook, System Biology Introduction Pathway Modeling. That's the one I use when I teach. We have this little tellurium antimony cheat sheet, which you should download. And there are many textbooks on dynamical systems, network modeling. Think of things like Uri Alon's book on networks. There's a nice online course at Caltech that you can access. There's really an enormous amount available online, maybe too much. Again, today we can only do the basics. So to begin with, I would like to start out by loading and running a model. We're going to start with the most simple possible chemical reaction. X goes to Y, Y goes back to X. The rates are called mass action. The rate of production of Y is proportional to concentration of X. The rate of production of X is proportional to concentration of Y. We're going to load a little CC3D program that has been pre-built that will load, run, and plot network models expressed in antimony. And then we'll see how to define models in antimony, and we'll run the model. Actually, how to define the models in antimony, we're going to do a little bit later. I've changed the order slightly today so that you don't have a lot of lecture before we do something. You're going to find out that all of our simulations, when we start building these complex simulations, are going to have 3 languages, not 2. You're used to CC3D, ML, and Python. We're now going to be adding antimony. And again, we will come to antimony syntax in a little bit. So I'd like everybody to download Tellurium v2 in the student materials folder. And this one, we're not going to code up by hand. All the other demos you can write on your own quite simply, but this one you need to download. We're not going to generate it. So please give me a thumbs up when you've got it downloaded, or if you're having trouble downloading it, please let me know right away. As usual, when you do the download, it's going to be a zipped file. Put it somewhere like your downloads folder, desktop, your CompuCell3D workspace. Unzip it and open it and twit it. Save it in a convenient location. Okay. So now, reminding you, opening it, you'll have to save it again. Once you've opened it, unpacked it, double click on it, open the file in Twitter. Now let's just look at what that code is going to look like. If you open the CC3D Python steppables, what you will see in it is a section that says model equals triple quotes equations J1 colon x goes to y, iterate bx, J2 y goes to x, iterate cy, parameters, initial conditions, and then below that variables, x, color of the variable, y, the color of the variable. Please run the simulation and give me a screenshot in the chat of what you see. Somebody, Nathaniel, put in an image which showed that there are no cells in this simulation, which is true and important. Remember, as I said, we're not going to be coupling the network models to cells today. That'll happen tomorrow. So you should have gotten something that looks like this. There's a comment here. There are no cells to display. Depending on how your player lays out, you may see a slightly different layout here. The simulation runs quite fast, so it'll go to something trivial after a while. And let's do something very simple in the Python. If you go to your CC3D Python steppables in your Twit, you'll see there are two lines here that are going to be relevant. We'll come back to the meaning of these lines a little bit later. But for now, we're going to try changing just two things. There'll be a line in the start function that says add free-floating antimony, and then it'll say step size is 1.0. And that step size controls the relationship between the network model time step and the CompuCell time step that says one network model time step unit is equal to one Monte Carlo step in CompuCell. If we make the step size 0.1, then we're going to slow down the speed at which the network model runs compared to CompuCell. So try making that change. Instead of step size equals 1.0, make it 0.01. Sorry, not 0.01, that'd be 100-fold, 0.1. And also, the size of the plot is in line 36. Plot win, add plots. The default plot windows, the default dot size is a bit small. Why don't you make it 8 instead of 5? Try that, run it, and give me a screenshot of the new result. It's a little easier to see with bigger dots. I want to call your attention to a couple of things in CompuCell that are useful. Some of the fancy features for CompuCell plots don't actually work. Some of them will crash player, I'm afraid. But there are some that work very nicely, one of which is export. If you hover over the window with the plot, you right-click and select export, you can export the plot either as an image, an SVG, for example, or as a CSV that will output the actual time series. And so while if you're going to be doing this for production, you might want to write file handling to output your data set. If you don't know if you're going to need it, it's a pain to have to write the file handling. And so being able to save the data from the plot is quite convenient. So I want to remind you of that. Now I'm going to back off and talk a little bit about networks, quant networks, in a biological context, and then how to implement them. There are a number of different kinds of biological networks that are important, quite a few really. chemical and reaction and metabolic networks that create and destroy the chemical components of cells and tissues. These would be things like enzymatic reactions, synthesis reactions. Those typically operate rather rapidly, milliseconds to second timescale. A lot of them happen inside of mitochondria. Then we have signaling networks that transfer information from the outside world to inside the cell, then within the cell. Those typically happen through both molecular transport and phosphorylation cascades. Those typically have timescales of seconds to minutes. We have gene regulatory networks that turn genes on and off, or that is, turn the transcription of genes on and off in the cell. Those typically operate on a slightly slower timescale, minutes to hours. And then we have transport networks, as I've mentioned before, particular of the blood, moving molecular species around the body, but also there are also other kinds of transport networks. You could think about gas flow in the lungs. You could think about lymph in the lymphatic system. You could think about the fluid and material in the gut. These are all transport networks. Fluid in the bone is another transport network. That one's a little bit harder to represent as a network. But whole body distribution of material is typically something we consider if we're going to think about the context, for example, for drug delivery or toxicity. There are other kinds of network models, population dynamic network models, which de-emphasize the spatial architecture of tissues. Here we might have a model where we start with stem cells, they differentiate into semi-differentiated cells, those replicate and differentiate into fully differentiated cells. That could be an abstraction of what happens in a colonic crypt in the gut, for example. We typically won't use those very much because we're representing cells as agents, but it's important to remember how they work. And translating those kind of population models into agentic models is quite interesting. T.J. Segoe has published a couple of papers exploring how to do that in a formal way. So you keep all the parameter values the same, and also what the differences are in the results. In the context of drugs and toxins, we also have things called outcome pathways or adverse outcome pathways. In this case, some of these boxes might represent chemical species, but other ones might represent more abstract quantities like tissue damage, tissue health, and so on. And this is actually a whole field of its own. CompuCell models could use models of this kind inside of cellular components, but they could also be components of one of these models. So you could take out one of these boxes here and replace it with a CompuCell model. Similarly, in these PBPK models that I showed earlier, we might have a spatial model, for example, of the kidney or the liver that we would use to replace this non-spatial model, this compartmental model here. And we did that, for example, when we modeled liver toxicity. So those are really the main kinds of biological models that we're likely to run into. Let me give you just a very few slides thinking about some of the issues we face with models. In a lot of the modeling world, the first thing one thinks about is metabolism. As I mentioned before in the metaphor of the car, if the engine is working in the car, you may not care about the details. Metabolism is a little bit like the engine of the cell, keeps things going. If it's working right, in many cases, you may be able to take it for granted. When it's not working, of course, you can't take it for granted. On the other hand, signaling, how cells make decisions based on information coming to them from the outside world and their internal state, is something that cells need to do all the time. Typically, the network architecture for signaling networks is fixed over the timescales that we're going to be working about it. And so you're changing state with a fixed architecture. Inputs are usually molecular concentrations. Outputs could be molecular concentrations or cell behaviors. Very often, they translate information, chemical concentration, contact, this sort of thing, outside the cell into responses inside the cell via transmembrane receptors. Sometimes that involves actual physical transport of molecular species into the cell. Sometimes not. It may just be conformational changes on the inside of the cell. A particularly important concept and component in this kind of network is a kinase. Kinases attach phosphate groups to other molecules. That phosphorylation typically switches molecules from inactive to active states, occasionally the other way around. There also are phosphatases that take the phosphate groups off, and so those kinds of reactions are pretty typical. This is a classic MAP kinase cascade. You have MAP kinase, kinase, kinase. It's phosphorylated. That's the star, means phosphorylation. That MAP kinase, kinase, kinase transfers its phosphate to MAP kinase, kinase. Phosphorylated MAP kinase, kinase transfers its phosphate to MAP kinase. Phosphorylated MAP kinase then goes on to do other things. That kind of phosphorylation cascade is quite typical in signaling. You could ask, why do you need a cascade? Why not just go directly from the input arrow to the output? And the answer is that the response function to output to concentration of input changes a lot. Response to noise and temporal response changes a lot too. A lot of what we see in signaling networks comes about because of the highly noisy environment inside of cells. If you're going to be building signaling models, you might ask questions like, does an increase in the level of a growth factor in the cell's environment lead to the cell proliferating or dying? Does changing the number of receptors on the cell membrane increase or decrease the cell's ability, for example, to migrate in response to a chemical field? Does a mutation that affects the amount or binding affinity of a component of a signaling network increase or decrease the strength of the output for given input strength? And how does a mutation in the network lead to changes in cell behaviors that lead to disease state? That's a sort of a question at the higher level organization. So those are the typical kinds of questions we'd address when we're looking at network models. Now, I have not talked about how you infer network models. There's a whole very large literature on that, and we're not going to be able to really address that today. I encourage you to look it up. A network inference is probably the hardest thing. Going from molecular measurements to network inference is actually quite challenging because of the fact that you need dynamic measurements to infer networks and omics as endpoint measurements. However, there's been a lot that's been done successfully, but it's a field that's continually being updated. There are certain kinds of standard motifs in signaling networks. Complex formation, where two molecular components come together, phosphorylation and dephosphorylation, which I mentioned. There also can be ubiquitination, which leads to the degradation of molecular components. There are many molecular species that have multiple phosphorylation sites, not just one. It's not always understood exactly what the difference of function of all those different phosphorylation sites is. Computationally, they're quite difficult to deal with. Rule-based models are one of the ways of dealing with that, but that's assuming that each phosphorylation site is independent of the others. When we come to gene regulatory networks, we come back to the central dogma of biology. We start with DNA. We have transcription to RNA, translation of RNA to protein, and then potentially post-translational modification of the proteins. There are a lot of steps going from DNA to finished molecule. We have to edit the RNA. We have to transport the messenger RNA to the ribosome. The raw protein has to be edited and folded. There's post-translational modification. Then we have to transport the finished molecule to the site of use. Most models of gene regulation ignore all of that, and they say that if you turn the gene on, you get the protein. At the very least, we know that there are intrinsic delays of 5 to 20 minutes between the time a gene is turned on and the time you get any protein at all. And so that has to be taken into account, or should be taken into account. But it's actually rather amazing that these highly simplified Boolean models that people like to use of gene regulatory networks actually work. They work okay. They have their problems, but they sometimes work pretty well. You will see diagrams like this that try to represent gene regulation as if it were integrated circuit. In fact, the way signals combine is not anywhere near as simple as it looks in this diagram. However, it is true that transcription of a gene is usually either on or off. And so at a simple level, transcription can be thought of as Boolean, although the switching between on and off states means that you can have graded expression. Gene regulation usually changes the structure of the signaling and metabolic networks in the cell. And they typically control long-term cell functions like differentiation of cells, and major decisions like switching between the phases of the cell cycle or going between proliferation and quiescence. There are a standard set of questions you could ask: the rate of production of key molecules in different cell types or between species, effect of knocking in or out or mutating specific genes or gene regulatory regions, whether there are stable cell types during differentiation, embryogenesis, healing, or cancer, effects of drugs or on cell types or molecular levels, and the effects of the product of one of these genes on the cell behaviors. Notationally, you typically use this kind of image for gene regulatory networks. Here I have an inducer which binds to a DNA, turns the transcription of the gene on. It would produce messenger RNA that's then translated into protein. That's often abbreviated just as inducer promotes protein, or even just I promotes P. The lollipop arrow with the circle at the end is promotion. There are classic gene regulatory motifs: activation. The T arrow is repression. You can have multiple signals coming in, interacting to control whether a gene is turned on or off. You can have gene 1 produce something that turns on or off gene 2. A gene's product can turn on or off itself. There can be small molecules in phosphorylation that affect production of genes, turning on and off of genes as well. Again, we'll talk about in MABOS, we'll talk about making Boolean models of gene regulation, but you can also do that using the techniques we'll be talking about today. Transport networks are the ones we're going to talk about the least. Some years, Jim Sluka has given a nice talk on PBPK, physiologically based pharmacokinetic network models. Again, typically these represent the transport of material by the blood. At least in most people, the blood architecture is the same. There are a few individuals who have peculiarities in the way the heart is wired. You have transport of blood by the heart through the lungs, through the gut, through the kidneys, liver, and the other organ systems. And the classic questions in PBPK models are, if you have a molecule presented to you on the skin, in the gut, in an injection, how is that molecule distributed and eliminated from the body? Who sees what in terms of concentration? Typically, you're going to be asking questions like, what's the time series of concentration of a molecule in a particular organ after a dose? How does that concentration depend on the individual's weight, age, sex, cardiovascular disease? Does it matter, for example, for a drug, whether it's injected or swallowed? And how rapidly is the drug or toxin eliminated from the body once we're exposed? As an example, if you're doing cancer therapy, you want to have a high level of concentration of the therapeutic in the tumor, but you don't want it to get into the liver because they're toxic. you might design particular transporter dosing strategies that optimize that. Okay. There is a standard imaging language called System Biology Graphical Notation, SBGN, for representing all of the complexities of these molecular networks. There are other network representation schemas as well. SBGN is the one that BioModels uses. In reality, all of these networks work together inside of our bodies. 3 networks work inside of cells. Metabolic networks, signaling networks, and gene regulatory networks interact inside of cells continually. Without transport at the whole body level, we wouldn't have the cells in the first place. And so all 4 of these interact together. Let's start now just talking about chemical reactions. These are going to be the simplest concept that we can represent. I hope most people have had a course in chemistry at some point, and so you're familiar with the idea of a chemical reaction. Here I have 2 molecules of ADP going to be 1 molecule of ATP and 1 molecule of AMP. So this is basically a phosphorylation desphosphorylation reaction. Here I have some arbitrary chemical formula. 2 molecules of A go to B. 1 molecule of B makes 3C. C plus A can combine to make D. And you'll notice I've drawn these as reversible reactions in each case. When I write a chemical formula, I have the identity of the chemical species and their transformations in what's called the stoichiometry. How many molecules of A go into making B? How many molecules of B going into C? The nodes are going to represent molecular species. The node state is going to be either the amount or concentration of that species. In a more abstract model, it might be some numerical value representing something else like the replication rate of the cell or the motility of the cell. The links, the arrows, represent chemical transformations between substrates, inputs, and products, outputs. Links have associated with them a rate of reaction, VF, and that's not always written. The notation is pretty sloppy in many locations for these kinds of networks. Rate laws will depend on the concentrations on the source side and possibly on things like temperature, pressure, pH, which we'll normally neglect. The fundamental concept of chemical reaction is a rate equation. Suppose A plus 2B makes 3C. 1 molecule of A and 2 molecules of B combine to make 3 molecules of C. We want to know the rate of production and the amount of C as they depend on the amounts of A and B. So the classic way to do this would be assuming that the concentrations are high enough that we can neglect individual chemical reactions. And that is called reaction kinetics. And here I've written A plus 2B goes to 3C at a rate VF, V forward, that depends on the concentration of A and B. We will often interpret rate laws as continuous processes, as ordinary differential equations, in which case this would become the A by dt is minus VF, the B by dt is minus 2VF, and dC by dt is 3VF. In fact, chemical reactions are discrete, happen one at a time, and so people might use something like Gillespie method or molecular dynamics. At the very end of this lecture, I'll show you Gillespie approaches, which are possible in CompuCell. Okay. Once I have that basic idea, to go any further, I have to have a hypothesis about what the rate law is. How does the rate of production of C depend on the concentrations of A and B? The simplest assumption is what's called the law of mass action. That is, that the rate is proportional to the concentration of the substrates. And if I have 2B, I count substrate B twice, so I have A times B times B, AB squared. There are other common rate law forms, which would be Michaelis-Menten and Hill, among others. And those rate laws are general, and those will work whether I'm doing reaction kinetics, Gillespie, or Boolean models. This is a little bit about thinking. We have two kinds of fundamentally different concepts of what an arrow is. People are often sloppy about this. I will try always to use a pointed arrow, a barbed arrow, to represent mass transformation. Activation and inhibition don't use up the activator and the inhibitor, and they use different arrow types. They use the lollipop for activation and the T for inhibition. So here, for example, I have molecular species S1 that's being converted into molecular species S2 that's activated by A. That means the rate of production of S2 increases as the concentration of A increases. Here we have A inhibiting S2. That's interpreted as nothing goes to S2 inhibited by A. In this case, activated. I said inhibited. Here we have A, and it activates S2. This is written like this. We interpret this as nothing goes to S2 activated by A. Again, the rate of production of S2 increases with the concentration of A. Inhibition, we have R inhibiting the production of S2 from S1. The rate of production of S2 decreases as R increases. R inhibits S2 directly, is interpreted as nothing goes to S2 inhibited by R. Again, the rate of production of S2 decreases as R increases. The key thing is that chemical reactions use up their substrates. Regulatory reactions don't. This is a slightly advanced topic, but I just want to give you one slide on it, which is if you look in the literature, you will see, for example, databases like KEGG, you will see lots and lots of diagrams that look like these arrow diagrams. They, in general, will not have functional forms for the reaction rates, and they very often won't have parameter values either. It's possible in a completely mechanical way to translate a statement like A promotes S2 or A promotes the production of S2 from S1 into a rate law. When you see activation, we know that for very small levels of A has very little effect. We know that if we have a lot of A, it doesn't change the rate at all. That means that this rate law will be sigmoidal. It'll be flat for very small values of A and flat for large values of A. And the classic way to represent those sigmoids is what's called the Hill function. A to the n over k to the n plus a to the n. And so we can actually go from a diagram like this to a reasonable hypothesis about what the functional form is for the rate laws. Integers n here are in the Hill function. Those represent the steepness of the sigmoid. And that's a topic I'd love to have a slide or two on, but I don't think we're going to have time to talk about it now. Small n, at n equals 1 would represent Michaelis-Menten, in which case the rate of effect of A is biggest actually when A is small, and then decreases as A gets bigger. N much bigger than 1 represents a switch-like behavior where for small A less than Kn, the circuit is turned off, and A bigger than Kn, the circuit is turned on. So that's a Boolean model. So N takes you interpolation between a linear model for small values of A when N is 1, and a totally switch-like Boolean model when N is very large. PBPK mathematics is all linear transport. It basically calculates the rate at which material is transported back and forth between two compartments. And you get a whole series of cascading linear reactions here. The only thing that's important to note here is that all of these look like rate laws. We have d amount on the left and some function of the amounts on the right. And there's a rate constant kf. I want to show now how to represent that very simply in antimony. Antimony model syntax only has 3 key components. That's why I like it. The first thing is that you have to represent your model. And your model is simply a string of characters. It's text. And in Python, we have to put text which has carriage returns in it inside of triple quotes. We can either use triple single quotes or triple double quotes. They have to match. So an antimony model is just a text string. Inside of that text string, we have the model itself. It's a model spec. And here are the rules that we have. Double slash or hash is a comment. Could be on a separate line or at the end of a line. Semicolon represents breaks between sections. It can be used instead of a new line character. If people are familiar with C++, they'll know where that came from. Value colon names a rate law or an event, and it creates a variable that has the value of the rate law. One thing that's important is that you can't name two things the same. If I name two things J1, you'll get unstable results. Antimony was originally designed to write chemical reactions, so its primary way of specifying models is in the form of chemical reactions. X goes to Y at a rate Bx. Y goes to X at a rate Cy. There are no double-headed arrows. Everything is unidirectional. So if I want bidirectional reaction, I have to write that as a forward reaction and a backward reaction. Things are very simple here. I write the name of the reaction, which is optional. I don't have to name it. X dash caret Y. X goes to Y. So X arrow Y. Semicolon the rate law. Semicolon. And that's all I have to do. If I have stoichiometry, so suppose 2 molecules of X went to 1 molecule of Y, I'd simply put a 2 in front of the X. So I essentially type my chemical reaction just as it's written here. The only thing that happens is that the Bx, the rate law, gets moved to semicolon and the end of the line. That's all I have to do. Couldn't be simpler. So here, X goes to Y at rate Bx, X goes to Y at rate Bx. Y goes to X at rate Cy, Y goes to X at rate Cy. Note that each line here, J1, affects 2 ordinary differential equations. And you could say, well, why not write the ODEs to begin with? The answer is that the network uniquely determines the ODEs, and the network can also uniquely determine a Gillespie or a Boolean model. If I give you the ordinary differential equations like this, you cannot infer what the network was that generated them. So ODEs are never a good way to represent mathematical biology because they lose information. They're highly ambiguous. The antimony specification is completely unambiguous. As I mentioned, we can have complex chemical reactions. Here, 3A plus 5B goes to 1A plus 2C plus 9D at a rate, this is actually mass action, K times A cubed times B to the 5th. In antimony, this would be written, here's a reaction, the name E2, 3 molecules of A plus 5 of B go to A plus 2C plus 9D. Antimony will automatically handle all of the conversions due to the stoichiometry. It's okay to have A on both sides of the equation. That's allowed. And in the latest versions of antimony, The stoichiometry can be variable in some cases. You can actually replace 3 by a variable name, although we're not going to do that here. Because antimony inherits from C++ rather than Python, the exponentiation operator is a caret rather than star star. And since we exponentiate things quite a bit, you have to remember that. It's easy to type the wrong one. If you've been working in antimony, you'll type caret inside of Python, which won't like it. If you've been working in Python, you'll type star star inside of antimony, which won't like it. So this one antimony line here generates 4 ODEs. So it's quite a powerful and compact syntax. All parameters in the model need to be specified, otherwise it's a syntax error. And so we have parameters b equals 0.1 semicolon. It's a good idea in comments to include the parameters units as comments. Initial values should be specified. Antimony won't crash if you don't specify them. It'll assume 0, but it's safer to always use specification of initial conditions as well. There are a couple of things that we need to know about antimony. If we don't care what produces A, we have a constant rate of production of A, K goes to A, we write that exactly as we do in the chemical equation, E1 colon nothing goes to A semicolon K. That'll generate dA by dt equals K, constant rate of production of A. We can have first order decay, A goes to nothing. A goes to nothing at a rate K times A. That's called first order decay kinetics. That would be written E2 colon A goes to nothing at a rate K times A. If we have the same molecular species in multiple antimony reaction definitions, T, T here, I1 here, then in the ODEs, everything sums up, and that's done automatically. Something that's very important and a little bit unexpected if you're used to procedural languages like Python or C++, is that the order in which you do specifications doesn't matter. If I reverse the order of E1 and E2, E3 and E1, it doesn't change anything. These are what are called declarative languages. Antimony has some additional capabilities, quite a few, some of which are gone through in much more detail in my course, my full course on this, or the 2023 lectures. They're all talked about in the online documentation. You can write ordinary differential equations directly using T prime notation. Strongly discourage you from doing that. Another thing that you're going to have to worry about is because of the declarative form of this language, assignments made with an equal sign are evaluated only when an antimony model is loaded. So if I say K2 equals 3 times K1, K2 will have the value that 3 times K1 initially had, and it won't change. If I want the parameter K2 to change as K1 changes, I have to use colon equals instead of equals. And that tells antimony to update that evaluation continually in time. That difference between a static and a dynamic equal sign is not something that we're used to in a lot of programming languages. But we are used to having different kinds of equal sign. In Python, for example, the difference between a comparison equal sign, a double equals, and an assignment equal sign, a single equals. So this is a third kind of equal sign that we have to be aware of. Antimony also has the ability to write what are called events. These are discrete time processes that change something. Those could be based on any trigger we like. Event name, colon, at any logical expression, colon, what happens. In particular, usually changes of parameter values. So if we want to add 15 units to the concentration of A at time 15, we could write E1 colon at time greater than 15 colon A equals A plus 15. That will only trigger once whenever the argument goes from false to true. On the other hand, I could write something else, E1 colon at sine of time greater than a half, B equals B plus 0.5. That will trigger every time sine of t goes from less than a half to bigger than a half. You don't have to trigger on time. You could trigger on levels. You could have if b greater than 5, a equals a plus 15, for example. This is actually pretty powerful. We often will do this kind of rule-based intervention in the Python layer in CompuCell, but sometimes it's really important to be able to do that inside of individual cells. Okay, now let's actually go and do some examples with a simple syntax. Remember the code that we just loaded. Let's open up that code, look at it. Now it maybe makes more sense. Here's the model definition. Model equals triple quotes. J1, x goes to x, y, rate b times x. Y goes to x, rate c times y. Parameter definitions, initial condition definitions. Let's try changing parameter c equals 0.01 to 0.1. Run that and see what happens. You could put them in the chat. Okay, that looks great. Why don't we just take a minute, try changing the values of b and c different ways. You could speed things up, slow things down. The ratio of b to c will determine the equilibrium concentration between x and y. If you play with that, you'll see that. So the ratio between b and c determines the ratio between x and y at long times. If I multiply both b and c by a constant, I'll speed things up or slow it down, if depending on whether the constant's bigger or less than 1. So you'll see that when you change c as a b, as I say, the equilibrium values, and those are usually written with a star, y star, and x star, will change. And you could play with this a bit more, if you like. Now let's do something a little bit more challenging. I want you to, I'm sorry, this says 5.1, it should be 6.1. To write a simulation of the following chemical reaction. A goes to B, B goes to C, C goes to D, at rate Ka times A, Kb times B, Kc times C. Start with a 10 units of A, 0 of C, and B, C, and D. And you'll have to change under variables. You'll have to change, here we had X and Y. You'll have to change it to A, B, and add C. Okay. And to begin with, you could try Ka, Kb, and Kc all equal to 1, 10, and 100. So I'll give people a few minutes to try that. Again, when you've got it working, put it in the chat. If it's not working, you can ask for help. Try it first and then ask for help. If you really get stuck, the finished thing is online, but this one you ought to be able to figure out on your own. If you could do this simple example, you can do much more complex things as well. It's not, you have to do more, but it's not harder. There's a good question in the chat. How do we do inhibition or promotion in this notation? Inhibitors and promoters change the rate law only. They don't actually involve reactions. Therefore, an inhibitor or promoter will show up as a change in the rate. So for example, if X goes to Y, we're modulated by chemical species A, then I'd write X arrow Y semicolon B times X times, for example, A divided by K plus A. Should be Michaelis-Menten dependence on A. So yes, inhibitors and promoters don't actually show up in the arrows themselves. If you're done with the basic part, you could try changing the values of Ka, Kb, and Kc. Here I made them go up by a factor of 10, making them go down 1.1.01 is also quite interesting. The shapes of the curves are very different. And having them all equal, K, Ka, Kb, Kc all equal to 1 is also quite interesting. You can have what are called sequential reactions, simultaneous reactions, a whole variety of different situations. If you want to go a little further, you could have a cascade that goes further. D goes to E, E goes to F, F goes to G, G goes to H, H goes to I. When you have that kind of cascade and you use this kind of geometric rate law for the rates, you get some quite interesting behaviors. Some years when we've had a little bit more time, we've explored that. But that's really something about networks more than network modeling in this context. But I'll say that that's a fun exercise to do. If you look in my full class, we spend half a day doing that particular example. You can definitely change the step sizes. Yes, well, these simulations, somebody says it looks wrong. These simulations run pretty fast, and in the end, you wind up with an equilibrium where everything becomes D. So typically, you want to adjust the time scale so that it runs a little bit slower, or just use step rather than run to do time stepping. Okay. So if you see something where you get where things happen too fast, you can change the time constant, as we discussed earlier. Someone put in the chat an image which has an error message. You'll see CVODE error, convergence failure. That should not be happening for the simple rate rules that we're specifying. But typically it happens when the time step is too big compared to the rates that you've achieved, or where you accidentally have a divide by 0, so one of the rates is divergent. So here's what I found when I ran this simulation. As I mentioned, if you try other rates, here's K1, Ka, Kb, Kc all equal to 1. People have shown 110, 100, and 1.1.01 as well. Okay, there are some annoyances in antimony. One thing is that antimony has reserved words, which you can't use as variables or parameters. For example, time and gamma are reserved words. So name parameters something like gamma 1 or delta 1 rather than gamma or delta. Missing an extra parentheses or improper separators tend to cause tellurium to crash with uninformative errors. Because the model is just a text string, it doesn't have line numbers in it, and that makes debugging it a little bit more difficult. If you find that your antimony is generating errors on model loading, your best strategy is to comment out the entire model, make sure it loads, and then uncomment the variable initializations, then the parameter initializations, and then uncomment the rate laws one at a time. And that's going to be the fastest way to catch reserved words and unbalanced parentheses. Again, because there are no line numbers, finding where an error occurs is not so easy. Now I'm going to talk a little bit about integrating antimony with CompuCell. We're going to have to learn how to load models and step them. Integration is through Python. We can load antimony models into the entire simulation, it's called free-floating models, or into individual cells. All antimony parameters and variables are CC3 dictionary entries. They're readable and writable. We don't have to do a get or a put. They're all there. But they do show up as dictionaries, and sometimes we wind up having to copy from one dictionary to another. In particular, if you want to do tracking fields, the tracking fields will have to copy the value from the network into the tracking field dictionary. We have to be able to time step the antimony model. We have to decide whether to solve the antimony model deterministically or stochastically, and we can also do some parameter adjustments on the network solvers themselves. TWIDIT has the code snippets. They're under the heading SBML-solver. That probably should have been changed to network solver, because the reason it's SBML-solver is that the first network specification language we supported was SBML. Nowadays, we support lots of different kinds of network models. If you go into TWIDIT SBML-solver under Python, it'll give you a bunch of options: model initial data, add antimony models, and so on. Let's look at the code that we have here. Your line numbers may be different. We have a specification of the model. We have a specification of the variables we're going to plot. And now if we look in the start function, we'll see self.add free-floating antimony model. Model string equals model. That was what we specified to read. Model name, we give the name a model. Give the model a name. Calling it model is probably unwise. And then give it a step size. In the step function, we have something that's going to plot the values here. And we have self.timestep underscore SBML. Self.timestep will timestep every model, every network model in our simulation. So the only way we can control the rates at which they step is through that step size definition earlier on. Okay, so again, the first thing we do is define the antimony model. That's a string. We can also load the antimony model from a file, or we could have the model specified in SBML, CellML, or MabOS, or BioNetGen. Then we need to load the model specification, self-add free-floating antimony model. Free-floating antimony model loads a single copy of the model specified in the string model, names it model string equals, and gives the time step. We can read from a file. There's a file read option as well. And we can load into individual cells. We can load different models into different cells. The models are independent in each cell. Okay, so we now time step the model. There are a series of options for the integrator. If you look, set SBML integrator global options, self.get SBML underscore global options. This allows you to set the tolerance for the solver. There's a relative and an absolute accuracy requirement. There's a number of steps allowed before the convergence fails. There's a STEF option, which changes the nature of the solver as well. If you're getting a lot of C-vote errors and you do not have a typo that's causing a divide by 0, then relaxing the accuracy of the model or increasing the number of steps or changing STIF to true are options to try to get around that. Typically, that happens when you have very rapid changes in value in your rate loss, which typically are not biological, although they do occur in things like action potentials. Okay, to read and write values from antimony models, it's very simple. Self.sbml.model dictionary key returns the value of the antimony variable with the name contained in the key. So if I say A underscore CC3D equals self.sbml.model quote A, that will return the value of A in the network. Note that the word model here is whatever name I gave my model here under model name. If I'd called it artichoke here, model name equals artichoke, it would be here would be self.sbml.artichoke square bracket. So I can have multiple dictionaries for different networks. To overwrite the value in the network model, I say self.sbml.model name handle key name equals new value. That's it. No gets and puts. Okay. So summarizing, if I'm talking about the global, self.sbml.model handle variable name. If I've loaded things into cells, it would be cell.sbml.model handle variable names. If I have declared a rate J1 colon, those cannot be overwritten, but they can be read. So rate equals self.sbml model J1 will give me the rate of reaction J1. I can't write to it. It's a read-only option. Okay. So now let's do another exercise. This is going to continue the one that we just did. Instead of having we had A goes to B, B goes to C, C goes to D, D goes, sorry. We had A goes to B, B goes to C, C goes to D. I want you to add one more line. D goes back to A. So this is now a closed cycle. And I want you to add in the Python a line that changes the value of Ka from 1 to 2. And I want people to run that again. If you get stuck, you can download. And please put the results in the chat when you have them. So you're adding one additional rate law, J4, D goes back to A. And now in the start function, you're going to overwrite the value of Ka. Okay, I see people getting this to work. If you've got it working already, you could try changing the initial values of A, B, C, and D inside of the Python or inside of the models, the network model specification. If you wanted to be adventurous, you could also try, Shivani didn't get anything. That's interesting. Wonder what happened. Did you start with your initial value of A not 0? If you want to be adventurous, you could look back at that event definition at time greater than 10, or in this case, probably at time greater than 2 or 300. You could say A equals A plus 10. See what that does. I had talked about events. An event would be something like at time greater than 200 on. It's pretty quick and easy to start playing with this. And again, if you want lots of nice examples, go to that Tellurium, read the docs. So beautiful examples there. Okay, here's what I got. And you can change the values of parameters. Ka equals 10, or K equals 2 or 1. You can do that either at the beginning or at any time during the run with the Python. You could change the initial values of B and C. You could change the rate constants, KB, KC. So you can change them in the initial model definition. You can change them using events inside of the model definition, or you could change them from CompuCell Python. You have 3 ways of doing that. Okay, the last thing I wanted to talk about today, well, great, somebody did that A plus A, that A example with the steps. You'll notice that the events trigger every time the argument goes from false to true. So if A goes from being bigger than 5 to less than 5, it adds 5 to A. And then A starts going down again, and it'll trigger again. So that's an interesting one. So you could build some very complicated circuits. These kinds of declarative circuits are very different from what you're used to thinking about in procedural languages, but they're quite important because biology doesn't really have if statements or loops. Everything happens at the same time. Maisha had a crash. There's a good question here. If I don't identify parameters in the model, is it possible to assign them in the Python code? The answer is no. You must specify all parameter values. They can be dummy values that you overwrite in Python, but they must be specified. Otherwise, when you load the model, it will crash. It's a requirement in Antimony that all parameter values be specified. Yes, so every 200 times, ADI gives code at time %200 equals 0, colon A equals A times 2. That will double the value of A every 200 time steps. Yes, you can be pretty ingenious about these things. Or you can have, for example, the sign of the rate law change from plus to minus under some conditions. You can write oscillators like that too. Can be a lot of fun to play with the event handlers. Great. So the last thing I wanted to talk about today, and I think we'll have just a minute or two to do this one, is stochastic models. If we're dealing with chemical reactions where we have lots of the molecules, then treating them as continuum is a reasonable approximation. However, a lot of important biological molecules have very few copies. For example, there's one DNA molecule for a gene, or a few transcription factors. In that case, fluctuations could be very large, and the ODE rate laws could predict the results rather poorly. CompuCell supports a Gillespie stochastic solver. It's a lot slower than the ODE solvers. The other thing is that the reaction equations specify the probability per unit time that one molecular reaction occurs in the reference volume. And that means that we're actually counting the number of molecules instead of, say, the concentration in millimolar. And so we need to be sure that our numerical values of all of our concentrations are bigger than 1, and our rates are less than 1. If our rates go big compared to 1, it'll crash. If the concentrations go below 1, it'll crash. Okay, how do I make this change? When I load my model, I add comma integrator equals quote Gillespie. That's all I have to do. I can even have Gillespie and ODE models running simultaneously inside of a single cell, although I have to load them as separate models, but I can do that. I also need to rescale the time step size by the number of initial molecules to keep the time series in register. And so I would use step size equals 1.0 divided by the numerical value of the concentration. So now let's do our last exercise here. In the code that you've been playing with, under initial conditions, change A from 10 to 100. And add in the line where we loaded the model, add comma integrator equals Gillespie. Make those two changes and run it, and put the results in the chat. And if you've got that done and other people are waiting for other people, you could try changing the initial values of A to 1,000 or 10. You could also change the rate constants to be smaller, 0.1, 0.01. So you're only initially making two changes, the initial value of A and adding comma integrator equals Gillespie into the model load. Let's see what you get. It doesn't look very much like the ODE model, does it? Now, if you make that initial value instead of 10, you make it 1,000 or 10,000, it'll look closer to the ODE. There's a question, is this a Monte Carlo method? Absolutely, it is a Monte Carlo method. So in this case, you're running a CompuCell is intrinsically Monte Carlo. It's a Potts model algorithm is Monte Carlo, and now we're running a Monte Carlo method for the networks inside of that. So there's a question, is there a way to couple this as fields so we could have cells that secrete or metabolize the constituents? We have, as you'll remember, we have uptake and secretion where we can have the rate of uptake or secretion depend on a numerical value in our model. One thing we have to be careful about is conservation of mass. In other words, if we secrete an amount of chemical into the chemical field, we have to remember to subtract that amount from the concentration inside of our cell. And similarly, if we're going to absorb material from outside and put it into the cell, we have to have a conversion factor that converts the amount of the chemical that we have outside into the change in concentration inside. There's always a bit of a tension between using amounts and concentrations. Concentrations are what determine the rates of chemical reaction. However, when we're doing with things like fluxes, for example, uptake or secretion or transport in PBPK models, it's easier to deal with amounts. And of course, to convert an amount into a concentration and vice versa, we have to know the volume of the thing that we're putting it in, or the amount or the volume of material secreted or absorbed. And CompuCell, unfortunately, doesn't handle that by hand. You have to do that yourself. So, excuse me, CompuCell, unfortunately, doesn't handle that automatically. You have to do it by hand. Okay, great. So here were my results. This was the ODE result. Here was the Gillespie result starting from a value of 100. So as a homework assignment, you could take this same model, load it into the global model twice. You'll have to give it a different handle when you do that. And then plot these two things over on top of each other to compare them. Does that sound like an exercise people could try? Is it clear what you need to do? You don't have to re-specify the model itself because the model specification doesn't care whether it's Gillespie or ODE solved. But when you do the loading of the model, you have to load the model once with the ODE solver and once with the Gillespie solver. And again, you'll have to not call it model both times. You'll have to call it model 1 and model 2 or something like that, and then read and write from those. That'll give you a chance to have two network models running simultaneously, one Gillespie and one ODE. All right, and if you do that, you'll get something like this. And you can see that as the number of initial molecules goes up, you converge better. If the number of initial molecules goes down, you converge worse. Okay, so that's what I had for us for today. I encourage you very strongly to read up on network modeling from other sources. As I mentioned, there's that great Caltech course. There's the Uri Alon course, textbook. There's Herbert's textbook. There's my online course material. I'd also encourage you to go to BioModels and do a little bit of browsing at BioModels and see what kinds of models are available out there. And with that, we have time now for questions, comments. Yeah. Oh, Nathaniel got the overlaying. That's great. See, it's not trivial to do. These things can become pretty complicated, but the basic syntax is not so bad, is it? You could do an awful lot very quickly. It's why I like antimony so much. It's really easy to learn.